Hey everyone, welcome back to my channel, and if you haven't already subscribed, this is a great time to hit the subscribe button. In the last video, I talked about how you can train your own StarDist based model and segment your images. And now you can take that model to segment whole slide images or large images. Of course, I'm not going to take exactly the same model I trained in the last video because that was an electron microscope image, and now I am dealing with a histopathological whole slide image. So for this, I need a different model, and luckily StarDist guys actually pre-trained a model on H&E images that I can definitely use right away to segment these nuclei in these images. So this is a whole slide image. And let us go ahead and jump in. And if you cannot relate to this, by the way, I should mention, if you cannot relate to what a whole slide image is, if you come from some remote sensing, some other background, I still encourage you to watch this video so you get good ideas in terms of how you can implement this for your specific type of research or job. And the key with StarDist lies in the object shape. The objects need to be convex, in other words, or star convex. In other words, the objects need to be roundish, or they should not, or if you're sitting in the center of these objects, you should be able to see every corner of it, every border, every point of the border. They're like kinks and turns, then this is not the right way. Watch the video before the last one to get a better idea in terms of what StarDist is. And also, if you don't have that type of patience, go to their page. And I'm going to show that to you in a minute. In fact, in a second. I'm right here. So go ahead and look at StarDist. And what I'm talking about is, do they have an image right here talking about what star convex is? No, but just trust me. Your objects, if they are rounded like these, you can easily segment them using StarDist. Okay, so with this information, let's jump in. And again, it uses a backbone model. It can be unit. By default, I believe it is unit. And it will be training a unit model. But instead of predicting the masks, or segmented image, it's actually predicting these two right there. Okay, it's a different approach. Go ahead and read the paper. Very interesting read. So let's go ahead and jump into the code. And I downloaded a whole slide image just by Google searching. Again, I cannot share that with you guys. It does not belong to me. I just downloaded for a whole slide image. It's tough to find, but go dig it. If you already have it, great. So first thing first, I need to make sure that I am using GPU. Otherwise, this can be a bit slow for large images. And let us go ahead and pip install StarDist. I'm showing this in Google Colab. So hopefully sometime around May 2022 timeframe, I'm recording this. Probably you'll see this sometime in June timeframe because I still need to edit this and schedule it as part. There's a lot of stuff that goes into publishing a YouTube video, but probably you're watching this sometime in June timeframe, so it's probably relevant, relatively current for you. Okay, so that got installed. So let's go ahead and install something called Image Codex. Again, on Google Colab, if you install this, it gives you the flexibility of reading and working with TIFF files and images that are non-JPEG and PNG, not the standard ones, but these special images. So those codecs can really help you. Otherwise, you may run into some error and you don't know why you're getting that error, and it takes a while. So trust me, install this. And the next set of lines of code, again, if you watched my last couple of videos, you probably recognize many of these. Nothing pretty deep. I mean, I can't, there's nothing that requires extra explanation that I haven't covered in the last couple of videos. Yeah. So these are the standard libraries. And now let's go ahead again. By the way, 90% of this code is from these guys' tutorials at StarDist. If you don't like me talking about this, if you just want to get the code, go ahead and go to their page, look at all the examples, because I'm only covering a subset of those examples, and get more information. If you learn from videos, obviously feel free to watch these and get the code, my version of the code, which is 90% similar, like I mentioned, from the link below, from my GitHub page. Okay, so I am going to run this function to show an image. It's basically, hey, if you get an image with some arguments, go ahead and plot it. That's pretty much it. And I am reading an image with an extension of SVS. And this is, I believe, the Apereo format for the whole slide image, which is the most common one that you'll find outside. But it doesn't matter. Even if you have a TIFF image, that also works fine. So go ahead and read your images. This is a whole slide image. And again, what do I mean by whole slide image? If you don't know, this is like Google Maps. You can render it at multiple resolutions. It stores this information in a hierarchical format, and you can extract information at different depths, with the highest resolution and also at the lowest resolution, and work with those. So that's what these whole slide images actually mean. And these are pretty large because they are pretty humongous. So let's read that, and let me tell you how large this is. So if I look at image.shape, this is not as large as some of the ones that you will see, in fact, but still large enough. 38,000 pixels by 32,000 pixels by 3 channels. This is an RGB image, such humongous image. And show image, yeah? So this show image is that function up there. So let's go ahead and show the image. And it's going to print at multiple, I think that's all it's doing. Yeah. So if you look at this, it's going to print the image at multiple resolutions right there at these multiple resolutions. So we should see an image right here at all these different resolutions pretty soon. Yeah, there you go. And it took about 30 seconds to get this thing, but you can see what it's doing. This is the entire image. And now you zoom in. This is part of that image, like right around here. You zoom in further, like right around here, right? You see that structure. That's how it looks like. You zoom in further. Now you start to see some nuclear structure right there. You zoom in a bit more, nuclear structure, bit more, and finally this is the highest resolution. You have the nuclei that you can clearly see, and you have the background. Okay, so what just happened? Yeah, there you go. For some reason my web page decided to refresh, or at least this part of it, but there you go. So these are the nuclei, and our goal is to segment these nuclei. How can we do it? We can do that by using a pre-trained model that is provided by StarDist right there. HE stands for H&E image. So the nuclei are in they are in purplish color because of the H right there. And the background in the pinkish color is from this eosin, the E right there. Yeah, in case you don't know. Let's go ahead and download the model. So let it download it. And let us go ahead and run this normalizer. It's basically another function to normalize this at different scales. So let's go ahead and do that. And I'm just defining the class for that. So let us help model.predict instances so we can see exactly on instances big. In the previous video, we did model.predict instances. Here, I'm introducing a new term. Well, StarDist guys did the job. I'm just bringing it in front of you, called predict instances big. If you want to understand a bit more about it, go ahead and help model.predict instances. That's exactly why I left that line right there. And then it kind of explains every little detail about what this is, and axis YX, and what does the block size mean, what the minimum overlap means, and all that information is right here. Very useful for you to go through. I'm following exactly that. I'm doing model.predict instances, provide your image, provide your axes, the way it is, and the block size, and minimum overlap between your patches and context, and normalizer, what normalization method would you like to use. And that's exactly why we defined a normalizer as a separate class right there, so we can kind of bring that in. So that's what we are doing there, and number of tiles. So this is what we are going to use, and let me click on this. It may take a little while. I'll pause the video and we'll continue as soon as the segmentation is done. Okay, so finally, it took about 7 minutes, 13 seconds to perform the segmentation, but I mean, I'm pretty sure you're not surprised. This is a humongous image with hundreds of thousands of objects. So let's go ahead and look at how the segmentation looks like. So let's call our show image again to show our labels. So here I extracted labels and polys, or details, whatever you want to assign that to. And that contains the object information, and labels are the labels. So which gives us the labeled image. So this is going to be a similar plot to the one we just did. Let me kill this so it makes it easy for us to go back and forth. So it'll be a similar plot like this, except at each stage, I'm hoping to see our nuclei segmented. Yeah. So let's go down, and there you go. So you have millions of, sorry, not millions, hundreds of thousands of nuclei at various stages, all the way coming down to this stage. Yeah. So I don't know what this, ignore that message for now. Sorry. Okay. So now let us go ahead and look at some of these subplots. So there's a lot of plotting going on here. Okay, so why am I doing this? This is basically the object number, right? It starts with object number something, and it goes all the way down to whatever that object number is. I believe I have 200,000 some objects, and this is actually showing you the object ID or number all the way from 0 to 200 some thousand. And this is basically all objects randomly colored. Just a different view for us. Okay, now that's just looking at it is not going to do a good job, right? I mean, we need to quantify it. We need to figure out what is the size distribution. So how do we get those metrics? So for that, I absolutely love the region props as part of scikit-image. If you have a labeled image, all you need is that. So let's go ahead and import that library, and region props table stores the information as it suggests in a table. If it's just region props, you get like individual region props. So I like region props table because I can easily convert that into a pandas data frame right away. So I am providing my labeled image and the original image. So it gets the intensity information and for each of these objects. And what do I want to look at? The properties, area, diameter, mean intensity, and solidity. Like kind of gives me an idea of the roundedness. So let's go ahead and extract that. Okay, so this is one of the issues of working with very large data sets. It worked fine the first time I ran it. Now it says your session crashed after using all available RAM. So obviously when I click here, it's not going to work. I have to run entire thing one more time. Sorry about that. The only couple of steps that I did not cover here are once you get this region props, now I'm going to capture that as part of a pandas data frame and plot it. So once I capture as part of the data frame, now I'm picking area and then just using Seaborn to plot it. So those are the final two steps. I wish I could show that, and let me run this one more time and see what happened. And it all depends upon what's available RAM right there at the time you're running your Colab, or pay for it to get extra RAM. But I did this once. That's exactly why I have extra lines of code. But for whatever reason, it decided to fail on me right now. But let me run this one more time and flash the screen at the end to show you exactly how the result of these would look like. So thank you very much for watching this video. And do not forget to hit the subscribe button and wait extra few seconds. If I actually get the result, I'm going to throw the screenshot at the end of it. And thank you very much, guys.